Hello and welcome to Maths with Jacob. This lesson will focus on applying differentiation, part 5. A special puzzle to warm up the brain cells is on the next slide. The answer will be given at the end. Enjoy. What is the meaning of the following? Good luck with it and see how you go. Curve sketching. When we are asked to sketch a curve, we have much information available to us. The important thing is that we must find this information systematically before sketching the curve and looking at its important features. Example 1. Use the function y equals x cubed minus 3x squared to sketch the graph. Include information about the roots of the function, the stationary points, the point of inflection, and any other relevant findings. Solution. To begin finding the roots of the equation, we need to find a number which satisfies the equation x cubed minus 3x squared equals 0. This is quite straightforward here in this example because we can factorise as follows. So the factorisation gives us x squared outside of x minus 3 equals 0. It is easily seen that the roots are x equals 0, x equals 3. Now note very carefully, because there's an x squared here, the curve touches the x-axis at x equals 0. We'll see that later when we sketch the curve. Because the sign in front of the x cubed is positive, the orientation of the graph is known, as we will see on the next slide. To find the stationary points, find the first derivative. So this signifies the first derivative from earlier videos. So here's the function. Here's the first derivative, 3x squared minus 6x. And here is the first derivative factorised. So now we continue on the next slide. Now, here is the first derivative again factorised. We saw in an earlier video that stationary points occur when the first derivative is equal to 0. So if we let this first derivative equal to 0, that means we can have x equals 0 as a possibility and x equals 2 as a possibility. We now continue by looking at the exact position of the stationary points. These are just the x-coordinates of the stationary points. Now we're going to look for the y-coordinates. So, when x equals 0, the value of y equals 0. So you substitute x equals 0 in the original function. That gives you y equals 0, so one stationary point is 0, 0. You substitute x equals 2 into the original function. That gives you y equals negative 4. So the other stationary point is at the point 2, negative 4. Now we look at the nature of each stationary point. That means what is actually happening at each of these stationary points. Now remember, that's the first derivative. And here is the second derivative, 6x minus 6. Now, into the second derivative, we substitute the x value of the first stationary point. And that gives us minus 6. So you remember from the earlier video, that is less than 0, so the curve at the point 0, 0 is concave down. Now we substitute x equals 2 into the second derivative and we get 6. That's greater than 0, so the curve is concave up. Finally, to find the point of inflection, let the second derivative equal 0. So 6x minus 6 equals 0, therefore x equals 1. Now we can sketch the curve. And here is one of the turning points, remember 0, 0. Here's the next one at 2, negative 4. Remember that turning point here at 0, 0 is concave down. There it is here. And the other turning point was concave up. And here is the point of inflection, 1, negative 2. If you substitute 1 into the original equation, you get negative 2, so there is the point of inflection. And remember, that's where the curve changes its nature. It goes from concave down to concave up. Example 2. Here is the next function. Look at it carefully. Please take note of the negative sign in front of the leading term. That negative sign there. This gives us a clue about the orientation of the curve. Now we rewrite the function as this. So all we do is take the negative sign out. And that's exactly the same as the first function here. We've just taken the negative sign outside the brackets. Remember, we saw in an earlier video that if function a equals 0, then a was a root of the function, which meant that x minus a was a factor. Let's try x equals 1 and see what happens. So function 1, we substitute 1 into the original equation, and we get 0. So 1 satisfies the equation, so it's a root of the equation, therefore x minus 1 is a factor. Okay? Hence, we saw how we could use long division to factorize the polynomial. So x minus 1 is a factor. So we divide x minus 1 into the original polynomial. Now, I've left the negative sign out. We'll put that in later. We don't need that here. So when we divide x minus 1 into the original polynomial, we get x squared minus 5x plus 4. We just go through the procedure as before, no remainder. So the original polynomial is, here's the minus sign, here is the x minus 1, which is this one here, okay, and here is the x minus 1, x minus 4, which is x squared minus 5x plus 4 factorized. So here is the complete factorization. We can see that the roots are 1 or 4. See, 1 or 4. The curve touches the x-axis at x equals 1. Because you have 2 of those here, that means the curve touches the x-axis at x equals 1. We'll see that on the curve in a minute. To find the stationary points, let function dashed x equals 0. Now remember, function x was this. Function dashed x is this. Take the negative sign out and factorize. So the stationary points occur when x equals 3 and when x equals 1. Remember, the first derivative has to be 0. That's how you find the stationary points. So we let that expression there be 0, so x can be 3 or 1. Now we can find the exact position of the stationary points. So if we substitute x equals 1 into the original equation, we get y equals 0. So 1, 0 is a stationary point. When x equals 3 into the original equation, we get y equals 4. So 3, 4 is another stationary point. Now we look at the nature of each stationary point. That is, what is happening at each of those stationary points. Here's the first derivative. Here is the second derivative. Now, you substitute 1 into the second derivative, and we get 6. That's greater than 0, so the curve is concave up. We substitute 3 into the second derivative. The answer is minus 6, which is less than 0, so the curve is concave down. Finally, to find the point of inflection, let the second derivative equal 0. So minus 6x plus 12 equals 0, so x equals 2. And here is our curve. Here is a stationary point. There is a stationary point. Concave up, concave down. Here is the point of inflection. Here's a quick quiz to help you. Please check through the video at any time. The answer to the puzzle. What is the meaning of the following? Easy on the eyes. That's a cute one, isn't it? Here are the answers to the quick quiz, and the video is at your disposal.